Right. In this session, I'm going to introduce another integrative technique referred to as integration by parts. Or as your textbook refers to it as anti-differentiation by parts. Same deal. Last time, talked a little bit about another technique of integration by substitution. And so this is just another technique to deal with integrals that you might not be able to talk about antiderivatives in a nice, easy, straightforward way. And I'm going to introduce the integration by parts formula. I'm not going to show how it's derived, although this is sorted out a little bit on page 345. It effectively comes from integrating the product rule from derivatives. And when you do that and do a little bit of rearrangement, you can come up with the following relationship. The integral of u dv is equal to uv minus the integral of v du. And in this case, u and v are both functions of some common variable. U and v are functions of a common variable. And I will get right into a couple of examples of using this. Example 1 off of page 345. We are asked to integrate x cos x dx. Now you'll often see integration by parts come up when you've got a product of two things as your integrand, because you can't just take the antiderivative of x and the antiderivative of cosine and cram them together, because if you were to go back the other way to take the derivative, the product rule would spread that all out. So we need typically some special technique to do that. Substitution will work in some cases, but in this case there's no nice substitution that comes out here. So I'll go with integration by parts. And I'm going to let u equal x, and I'm going to let dv equal cos x dx. So what I've done is I've basically broken up the parts of the integrand and assigned them to u and dv from my integration by parts formula. Often how we will choose to do this, although there's no hard and fast rule for this, but u will often choose to be something that we can nicely take a derivative of and make life a little bit simple, whereas dv will try to stick with something whose antiderivative doesn't overly complicate things. I'll often say that dv will involve something that has a bit of a cyclic derivative, if you like. Derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is positive sine, and then it just keeps cycling through those. E to the x is also a nice common choice to have involved in your dv, because it's its own derivative and its own antiderivative. So the other things I would need to fill out my formula for integration by parts would be v and du, and I get those from what I've chosen for my substitutions here. If u is equal to x, then du is going to equal dx, fairly straightforwardly. And if dv is equal to cos x dx, then v was just sine x. Now I've got all the pieces I need to fill out this integral. Integral of x cos x dx, or u dv, is going to be u times v, x sine x, minus the integral of v du. Now the purpose of choosing my u and my dv the way that I did was so what I end up here with on the end is an integral that I know how to work with. I can find the antiderivative of just sine x fairly straightforwardly. So when wrapping this one up, x cos x dx equals x sine x minus, and the antiderivative of sine is simply cosine, well, negative cosine. And then, since these are indefinite integrals, I'll put an integrative constant on the end to represent the entire family of solutions. And so this is us stepping through integration by parts for a particular integral. It's very formulaic when you're first getting used to it. As long as you pick out a u and a dv, you can just drop things into the formula and keep working. Sometimes there's a bit of churning through to do. And occasionally you might need to do it more than once. As we will see in example 2, which is tight enough that I'll probably go on to another page. So, in example 2, on page 346, we are asked to evaluate the integral of x squared e to the x dx. So, my parts formula, again, is the integral of u dv equals uv minus the integral of v du. So I need to choose some u's and some v's and go from there. So I am going to let u equal x squared and dv equal e to the x dx. Again, in dv I've got something whose derivatives and antiderivatives look a lot like each other. In this case, exactly the same thing. And in u I've got something that gets more simple as I take its derivative. So du would equal 2x dx, and v would just equal e to the x. Putting that into my expression, I get u times v minus the integral of v du, or 2x e to the x dx. Now, the issue that crops up here that you might notice is that I'm not sure how to find the antiderivative of this thing. So, I get another integration by parts. I might choose to do that off the side. Integral of 2x e to the x dx. If I were just dealing with that, I'd let u equal 2x. So du equals 2dx. And I let dv equal e to the x dx, so v just equals e to the x. Churning through my integration by parts on just this little integral, I have u dv, or 2x e to the x. Sorry, I have uv, 2x e to the x, minus the integral of v du, which is just 2 e to the x dx. And I'm going to put this in for my integral here. Squared e to the x dx equals x squared e to the x minus all this. I'm going to stick that in brackets because I'm subtracting everything here. 2x e to the x minus integral 2 e to the x dx. Ooh, churning. Dx equals x squared e to the x minus 2x e to the x minus, and that is just going to be 2e to the x, since e to the x is its own antiderivative. And tack a constant on the end, and now we'll just resolve the signs. Integral x squared e to the x dx will equal x squared e to the x minus 2x e to the x plus 2e to the x plus a constant, which you might also see simplified by bringing the e to the x out of the first few terms and having x squared minus 2x plus 2 all plus a constant. These can take up a bit of room, particularly if you need to do it more than once within an individual problem. A few more examples. Example 3 on page 346 ties this a bit more into one of our initial value problems. We're asked to solve the differential equation dy dx equals x ln x, and for x equals 1, y equals -1. Okay, so I can rearrange this. Dy equals x ln x dx. I'm going to try to stop my lighting from going crazy every time I move my arm. One moment. There. Hopefully that's a little bit better. Alright, so if I integrate each side of this, the integral of dy is just going to be y, and on the other side I'm dealing with x ln x dx. As you might not be surprised to learn, I'm going to do this with integration by parts, but my u choice is going to be a little bit different here. If you've got a ln x involved, then often that's going to be your u. For this simple reason, an antiderivative of ln x is a little unpleasant, but its derivative kind of makes life a little bit simpler. Now that leaves my dv to be x dx, which would make my v a half x squared, which seems like I'm making things more complicated, but when I couple that with the 1 over x, it will actually make life pretty straightforward. So then following the integration by parts, uv, I get a half x squared ln x, minus the integral of v du. 1/2 x squared times 1 over x is just going to be a half x dx. And that's much easier to talk about the antiderivative of, and this ends up becoming y equals 1/2 x squared ln x minus 1/4 x squared plus some constant. Now, I still have the initial condition to solve. At x equals 1, y equals -1, and that will let me figure out what this integrative constant at the end should be. So -1 equals a half of 1 squared ln 1 minus 1/4 of 1 squared plus a constant. You might recall ln of 1 is 0, so I end up with -1 equals -1/4 plus a constant, or my constant works out to be -3/4. And ultimately I can say that y equals, and I might factor out, I won't factor just yet, 1/2 x squared ln x minus 1/4 x squared minus 3/4. I can make it a little tidier. I won't bother. Okay. Example 3. You get about 1 question a page. If you're a little tight, you might get 2 on a page. Well, I'm not going to in this next one. Now, example 4. It's from page 347. And we're asked to evaluate this thing. E to the x cos x dx. Now the immediate problem here is that neither of these things are going to simplify when I take their derivatives. You're just going to keep cycling through the same sorts of things. But in doing that, you'll actually find a neat little pattern. I'm going to rewrite this up here for reference. Integral u dv equals uv minus integral v du. Okay. Now, the first step, I'm going to assign these as my u and my v values. It doesn't really matter which one I choose where. I'm going this way because I find it a little bit easier to think about the antiderivative of e to the x than of cosine, because I don't have to worry about changing signs here or anything really changing at all. So, derivative of cosine would be negative sine x dx, and v would be e to the x. And if I step through my first phase of the integration by parts here, I would get u times v minus the integral of v du. Now I'm subtracting a negative, so ultimately I'll just leave it positive. And I have e to the x sine x dx here. So, off to the side here, I'm going to churn through this integral by doing parts one more time. I'll let u equal sine x, which means du is going to be cos x dx. And I'm going to let dv be e to the x dx, which means v will just be e to the x. Churning through the parts on this, I would have u times v minus the integral of v du, or e to the x cos x dx. And I'm going to put this in for my integral here. So I can say that the integral of e to the x cos x dx equals e to the x cos x plus e to the x sine x minus the integral of e to the x cos x dx. And then before you get caught in this rolling stream of continuing to do this by parts forever till the end of time, you might notice that, hey, this integral looks a lot like this integral. What if I just add it over to the other side? E to the x cos x dx plus integral e to the x cos x dx equals e to the x cos x plus e to the x sine x. Well, if I've got one integral of e to the x cos x dx and I add another integral of e to the x cos x dx, pretty sure that means I've got two integrals of e to the x cos x dx equaling this thing. And then if I just divide each side by 2, I have my result. Kind of seems a little cheap at the end of it all, but gets the job done. And as always, if you are having an indefinite integral, you stick an integrative constant out on the end of it. So typically this trick will come up when you've got a couple of different parts in here, both of whom have derivatives and antiderivatives that don't really simplify you any further. They just keep sort of cycling through the same thing. That's often when you'll see this trick getting used. I'm going to mention briefly here in reference, but I'm not going to do much with it. Examples 5 and 6 refer to something called tabular integration. It's really a shortcut for a time when you might find yourself using integration by parts multiple times. I'm not going to go through the process right now. It is just a shortcut through what we've talked about before, but if anybody wants to read up on it, that's tabular integration, which is a shortcut through repeated integration by parts. and it is outlined in examples 5 and 6 on pages 348, 349. If anybody wants to go a little further with that. Still going to do a couple more examples, because who doesn't love examples? Take a look at example 7 on page 349. Here we're asked to evaluate the integral ln x dx. And where it looks simple, sometimes that's not always how things work out. And I would challenge you to just off the top of your head come up with the antiderivative of ln x by the rules that we've talked about. So we'll attempt to do this by parts instead. Again, if there's a ln x involved, that's probably what we're going to have u become, which really just leaves dv to be dx. So if u equals ln x, then du will be 1 over x dx. And if dv is dx, then v is equal to x. Stepping through my formula for integration by parts, I have u times v, which would simplify to x ln x, minus integral v du, x times 1 over x dx. Well, the x and the 1 over x cancel out, so this just simplifies to x ln x minus the integral of dx, or x ln x minus x plus a constant. My last example, which kind of combines this integration by parts with integration by substitution that we looked at before. Example 8 from page 350, where we are asked to deal with the integral of the inverse sine of x dx. If we let u equal inverse sine of x and dv equal dx, then you might recall from before the derivative of the inverse sine of x comes out to 1 over root 1 minus x squared, and v in this case would simply equal x. Stepping through my integration by parts formula, this becomes u times v minus the integral of v du, or x over root 1 minus x squared dx. Which might look unpleasant, but if you've had a chance to practice some of the substitution, you might notice that the derivative of 1 minus x squared is going to look pretty similar to x. It'll have the same power of x involved. So I'm going to deal with that integral by substitution. I'll let u equal 1 minus x squared. Then du would equal negative 2x dx. Or, if you like, x dx equals negative a half du. And x dx is what I've got right here. So with substitution, the integral becomes, all of this inside the square root is u, so this is u to the minus 1 half du. And I've got a much easier way to deal with that as an antiderivative. I should end up with a u to the 1 half times 2 plus a constant, or 2 root 1 minus x squared plus a constant. That's going to come back up here, and I can say the integral of the inverse sine of x dx is equal to x times the inverse sine of x minus 2 root 1 minus x squared plus a constant. So that was some examples of working with integration by parts in a few different scenarios. There'll be even more practice on the Google Classroom site with this. That's all I have for now. Thanks for listening.